Good morning. Welcome to 2014 Spring Student Outreach, sponsored by the Dallas chapter of the IEEE Reliability Society and the Department of Computer Science at the University of Texas at Dallas. Our speaker is Dr. Christian Hansen, who is professor and associate dean of the School of Computing and Engineering Science at the Eastern Washington University. He is also the president of the IEEE Reliability Society. Dr. Christian has published on a variety of engineering applications, mostly related to reliability modeling and failure data analysis for complex electronic systems. He received his master's degree in electrical engineering and a PhD in statistics from Technical University of Denmark. The topic of his lecture is drilling for useful information in the landscape of big data. Ladies and gentlemen, let's welcome our speaker, Professor Christian Hansen.
So now on a little bit about what I'm going to talk about today. So I'm going to talk about big data, and this is something I've been interested in over the last few years. I've been interested in data pretty much throughout my career, and as you saw from the opening slides, my background is in electrical engineering and in statistics. So my main research area is statistics. I analyze data, but I don't do mathematical proofs and that kind of thing. I like working with real world problems, and so big data is sort of one of the big buzzwords these days. I'm going to try to give it kind of the 10,000 foot view of big data. I want to talk a little bit about some history and some future challenges, and I'm going to really focus kind of on how do we drill for useful information. So a lot of the data out there, is not necessarily useful for what you're looking for. I call it finding the needle in the haystack, and talk a little bit about some of the challenges related to that. I'll talk a little bit about Moore's Law and some of the problems we're facing with that. What I'm not going to talk about, I'm not going to go into very technical details here, and that's just simply because I'm probably not the smartest person in the room. And with all the students I see here, you probably know way more than I do about the technical aspects of data mining and using Hadoop, MapReduce, those technical issues. So those I will not be going into. I will perhaps share some opinions. Those are my personal opinions. So even though I'm here as a representative for IEEE, just the usual disclaimer here. These are my opinions. So I will start up with sort of an opening quote here from an article that's going to appear in the IEEE Computer Magazine, and it's written by a good friend of mine, one of the co-authors, Jeff Vose, who was another one of our former presidents. And I'll read this quote here. So it says, "The challenge of mining these voluminous data for actionable intelligence is staggering. The sheer volume and multiplicity of relationships, whether derived from metadata or otherwise, require novel analytical approaches that in turn demand new mathematical applications that until recently were only theoretical side attractions for mathematicians." So I love that statement there, that those things that in the past were just things that mathematicians and statisticians did just for fun and didn't think anybody would ever think about applying it. Now the real world is coming back to haunt the mathematicians and the statisticians. We actually need some very novel mathematical techniques. So I call it the new intersection between math and computer science. Like many computer science departments grew out of mathematics departments. That's anyway was true where I have my tenure, but now they're kind of coming back together. So just a comment here for the students here in the room. There are some very big careers you can pursue in big data. I know many universities are offering degree programs in big data or data analytics, but you don't really need a degree with a specific designation. You can kind of build your own degree if that's something you want to pursue, and I'm pretty sure that UT Dallas have all the right courses you're going to need to build a successful career. If you don't believe me, just try to do a job search here and type in big data or data analytics. You'll see there are lots of great opportunities out there. So a little bit of history here. So the term big data, where did that come from? It's actually been around in the literature for quite some time. Concepts of big data go back way back. But let me talk a little bit about what we mean by data in general. And big data, or data, is defined, if you look in the dictionary, as sort of factual information used for reasoning, discussion, and calculation. That's sort of the classical interpretation of data. But when we talk about data, and big data in particular, we really have broadened that definition. So we often talk about big data as not just statistical data, but also electronic content in general. So the big data encompasses music, video, unstructured text, and a lot of other things. And of course, big data wouldn't be relevant if we didn't have cloud computing and advanced parallel computing techniques available. Just to put things kind of in perspective here, so I did my graduate work about some 20 years ago, and at the Technical University of Denmark, where I did my graduate work, we had these 3 computers. They were considered supercomputers at the time, but really they're probably no more super than the calculator you carry in your pocket. We had 3 machines, and each machine had about 24 to 32 megabytes, so not gigabytes, not terabytes, megabytes. The total hard disk space in the entire computing room, which was maybe a room half the size here, had about 5 gigabytes of data. So, on my iPhone here, I have about 6 times that memory capacity. So the old big is now the new small, right? But big data is really more than just large data storage. It's commonly referred to as the 3 V's that characterize big data, which are volume, velocity, and variety. And of course, what we consider a large volume is going to change over time. Certainly has changed since 20 years ago. But in general, it's a large volume if it exceeds what we can put on a single computer. It's large velocity if data is being generated faster than we can download it to a computer. So it's being generated fast. And there's a variety of data. So it exists in many different formats. So text, video, images, audio, and so on. Just kind of a little bit of overview here. Just to kind of put things in perspective of when we talk about big in terms of how we measure things. So we've gone from bits, to bytes, to kilobytes, where, in the old days when we were sending emails that were just text, to megabytes when we started sending pictures, and gigabytes when we started putting videos on our movies on our phones, and terabytes, that are now just, a standard cheap external hard disk, to petabytes, which are now, kind of what you talk about when you talk about servers or computer clusters, to exabytes when you're talking about entire data centers, to zettabytes, 10 to the 21st bytes, if you're talking about like measuring all the data that's out there on the internet. Digital world of data, it's predicted to be about 8 zettabytes by 2015. So, and it's growing roughly in accordance to Moore's law. And so Moore's law states that total volume doubles roughly every 2 years. And there's sort of a reverse version of Moore's law, like everything then becomes half the size in 2 years. So with hard disks that a terabyte hard disk tends to become half the size in 2 years. So data basically is cheap to store, and for that reason, we're not really very concerned about the cost of storage. And so we tend to keep everything, like unlike what we do in our basements. When we run out of space, we have to clean up, we have to get rid of stuff. And so data hoarding is becoming a big problem because we tend to keep everything. And I do that. I mean, when I buy a new computer, I just copy everything from my old one. And I don't have the time to go through and sort things. So I just keep everything. And that's pretty much how the internet and big data works, is we don't have the time and energy and the money to sort through things and reduce them. Big data velocity, just a couple of numbers here to kind of give us an idea of the type of velocity we're dealing. So like YouTube, 48 hours of video being uploaded every minute. There was a joke a few years ago where, as an April Fool's joke, they came up with buy a DVD that has the entire collection of YouTube videos. Nobody bought it. Well, Google, 571 new websites created every minute. 1 billion tweets every 2 hours. So very large amounts of data being produced, much larger than we can comprehend. In terms of variety, so when we talk about structured data, which is kind of how I'm thinking of data as a statistician, when I definitely prefer to work with things that are, have well-defined variables, a single format, tabulated quantitative information, something I can do traditional data analysis, but that's not how data exists in the world of big data. So variables are not necessarily defined. So we define variables as we do our data mining. We deal with multiple formats that are not tabulated. We deal with text, audio, video, and so the new data analysis is the data analytics. So other characterizations of big data is, instead of the 3 V's, there's the S's, your source, size, speed, structure, complexity, value. A fellow, Charles Fan, that works for VMware, gave the following characterization of sort of the classical data collection versus the modern data collection. So he says the old way of collecting data was we collect, we record it, we update it, and we delete it. So there's the cleanup here that we used to do. So he calls that the CRUD data, whereas the new modern data collection is we create data, and actually creates itself. It's primarily machine generated. We replicate it, we append it, and we process it, but we don't really delete anything. So he calls that, well, you get it, the crap data. So what will the next generation of internet look like? And so obviously big data and internet are traditionally connected. So the way I've always thought of the internet and how it originally was formed, like back in the 90s, was just a connection of computers. So it's a network of computers. We could call it the internet of computers, whereas the new internet is much broader than that. So traditional internet was, connected personal computers with, allowed us to do e-commerce, online purchases, connected on our mobile phones, and so on. But the new internet, which is often called the Internet of Things or the Internet of Everything, is exactly just that. It connects not just computers, but also things in general, most importantly humans. So the speculation is that in the next generation, not only computers will be part of the internet, but we ourselves will become part of the internet, which allows for a number of new things like a smarter energy grid, smarter healthcare, smarter just about everything. When everything has a sensor, everything allows us to produce, collect data. So as a result, of course, big data will become even bigger in the future. So just again, kind of an old world, new world comparison. So when we talk about useful information that we get from the internet, like traditionally we were just emailing, we were just like asking, well, how are you? I could send an email, I could get a response in the next day as opposed to writing letters. So that was useful. and then Google were finding things on the internet, starting to order things like pizzas online, getting directions, and even finding your iPhone, which is some of the newer gadgets, but it still really just resembles not the Internet of Things, but really just the Internet of computers. So like Find My iPhone, it's a nice little gadget, but it is pretty much just that. So I had a good friend from IEEE who left his iPad in the seat pocket on the airplane, realized quickly after, oh darn it, I left my iPad there. Let me go on my phone here, see where's my iPad. And my iPad's in airplane mode, and it probably by now has lost its power. So it's not really useful. It's not like the Internet of Things where things would actually have more useful identifiers. So some of the predictions of where the Internet and the kinds of questions we'll be able to answer will be like, where is my child? Not just where's my child's iPhone, but where is my child? Where's my husband? My wife might want to ask that question. Is my husband really in Dallas giving a talk? Who is he with? And so speculations might be that the Internet will be able to answer those things. And that can be good news and can be bad news. I actually think it's good news. So if my wife knows exactly where I am, they don't have to answer any questions that can be speculated. What's my heartbeat? So like, will the Internet be able to monitor my health? And I don't have to really necessarily go to a doctor. Not just giving me directions to where I need to go, but actually tell my car to drive me there, is what many people think of. And pretty much answering anything and about anything and everywhere. So there's some good news and some bad news associated with that. So obviously the good news is, as we all probably would agree, communication has been easier. A lot of us like to text people rather than talk to them. I had to have a conversation with my daughter the other day about, you don't text your boyfriend to tell him you're breaking up with him. That's not really what a smartphone's supposed to be used for. So texting shouldn't replace good old verbal communication. Big data has certainly made it easier for businesses to monitor their customers, find out what their customers want, and better do selective marketing for the customers. It's sort of a misnomer that it's given the consumers more choices. Now there's a company out in Seattle that started a few years ago called Decide.com, which had a fantastic concept, which was to use big data to help consumers find out how to get the best price on a product. So you could use say you're out shopping for a new car, use big data to search all data, on prices and cars being sold, and then you would have the models help you decide when is the best time to buy. And for a monthly fee, you could do that. You could save thousands, and the company could make millions. Even you pay $35 a month, that could add up. Now, that company ended up being bought by eBay. And so they like to give you option to decide. You can decide anything as long as it's on our shelf, right? So I think there are forces working against giving consumers full choice using big data. But it certainly is a possibility. Now, so some of the bad news is, obviously we're losing some privacy by having information available. Some husbands may not want their wives to know exactly where they are. They definitely don't want the government to know where they are. We lose some effective communication. Big data has certainly opened some new opportunities for cyber crime. And I personally worry about what will the next generation of cyber crime look like. So we all worry about getting our identity stolen, but what if somebody could actually hack into your heart monitor, or somebody could, hack into your car that's a self-driving car and drive it somewhere, and you're literally having your car hijacked. Those things are things that many of us worry about. And just the possible, will there ever be a choice, or will there be a choice in the future to truly be online. I still know people that don't own cell phones that rarely go on the internet unless they have to. Well, will that even be an option in the future? I was listening to this presentation here on YouTube a few days ago by John Barrett, and he talks about how big data and the Internet of Things what that might look like for healthcare. Like, will it look like this, that you get a message on your smartphone that says, your phone just called us and told us you're not feeling well, so we're sending an ambulance to pick you up. It could also be that, we see you're not feeling well, so how about trying this wonder drug here, and you click here to buy. Or it could be your phone tells us you're not feeling well, so your health insurance just went up by 25%. And those are all certainly possibilities, and that could be part of the bad news. And every one of us have followed over the last month the tragedy of the loss of Malaysian airline Flight 370. Now, big data plays a big role in that investigation, and ideally, big data would have solved the mystery a long time ago, because, as some of you know, airplanes transmit a lot of data. It actually falls in the classification of big data. So a single airplane dumps approximately 20 terabytes of data during 1 hour of flight time. That resembles roughly the amount of data being exchanged on Facebook, 500 terabytes a day. And that's for one single airplane. So you would think that with big data, that we would know exactly what the condition of the flight, the airplane was when it had a problem, where it went down, and temperatures and everything useful. But as you probably also know, at some point the airplane just stopped transmitting data. And now we're stuck with having to analyze satellite images, which is a much, much more complex application of big data. So there are lots of speculations. Did somebody maliciously turn off the transmission of data, or was it just a failure? In addition, maybe independently of the failure of the aircraft itself. So yes, big data is important when it comes to flight safety, but it's just like the Where's My iPhone app here. It doesn't work if someone can fairly easily hack in and turn it off, or if it only works if it's powered on. So we need some different technology that allows data to be constantly transmitted. So again, back to the conversation here about, does big data mean more useful information? So the assumption here is big data, or the digital world doubles every 2 years. Does that mean we also get twice as much useful information every 2 years? And my personal opinion is that we don't. Well, we're constantly searching for the needle in the haystack, but the hay is getting bigger. The needles aren't necessarily getting much bigger. Like, for example, there are about 30 million songs available on Apple's iTunes that you can download. Now, how many of those 30 million songs do you actually care to listen to? And so say that doubles to 60 million songs in another 2 years, you're probably not going to have twice as many of your favorite songs on there. I always ask this question, so what would Google and YouTube look like if it was operated by your TV remote? So like, we have so much stuff there on the internet and on YouTube, but it's only as good as the tools. Like if you had to actually search through websites with a remote, what would it look like? That's why I don't watch much TV, because I don't have the patience to cycle through 100 channels. Now, what if I had 10 million channels on my TV? They would need to come up with something more intelligent than the remote. So the tools really are necessary for us to extract the useful information. And in this project here by IBM, they talk about sort of 4 layers of data, or the internet here, so they call it the DIKW, data, information, knowledge, and wisdom, where wisdom sits on top. So out of all this data, how do we extract the parts that are useful? And out of the parts that are useful, how do we help us develop more knowledge and wisdom? So let me talk a little bit about the computing aspect. So in order for us to process big data, we obviously need to use more than one computer. And my first introduction to parallel computing came back when I was a graduate student, and we did a lot of simulations. And so back in those days, and the speed of those computers, if you did like 100,000 simulation runs of a model, it could take you 24 hours to do it. So we'd spread it out over 3 computers and then let them run overnight. In the morning, we'd merge them together into one batch. Now, so that's kind of the old school version of parallel computing. So it's an example of scaling. And so the assumption for us to keep up with Moore's law as data continues to double, the assumption is also that our computing power continues to double, because we certainly won't have double as much time to wait in the future. So scalability is a big question here. So to what extent can we continue to scale computing? So the idea of scaling means basically that you can reduce the computing time by a factor n if you're using n equally powerful computers. So it relies on the assumption you can merge the results. Computing time is often measured in terms of flops or floating point operations. And there are some problems that are easily scalable. So like the example I gave you with simulations, those are easily combined after we've spread them out. There are other problems that are not as easily scalable, and I'll show you an example in just a minute here. So iterative or recursive computations are not necessarily scalable. So if you have to do 1 million iterations of a model to get the desired result, you can't necessarily spread that over computers. Yahoo uses about 4,000 commodity computers in their network. So in my world, I do a lot of statistical modeling, and most of you are probably familiar with the concept of a linear model, where we try to find variables that can explain a certain output variable. And so in the traditional linear model, we work with matrices, and I'm not going to go into too much math here, but so this is kind of a key result in statistics, the solution to the least squares equation here, where you construct a matrix that basically represents your model, and the size of that matrix depends on how many variables you have in your model. So let's say I have a fairly simple model. I want to predict the price of houses. I want to use 10 different variables. Okay, I can take my data, I can crunch that in a matter of seconds. Now, with big data, I may have thousands, 100,000s of variables, and doing those types of calculations, even with multi or parallel computing, can be extremely complicated. So, like just some simple math here, like if you multiply 2 matrices, that requires, if you have matrices of these dimensions here, n times k and k times p, that's going to require k times p times 2n minus 1 flops. Now that's fairly easily scalable, so you can do them, one element on different computers. Now if you're talking about inverting a matrix, that's more complicated to do, to spread that calculation over different computers. So like, to invert a k by k matrix, if you use traditional, if you look in your traditional linear algebra book, that's going to require k to the 4th flops. So that increases very rapidly with the size of the matrix. There are some techniques that can reduce that, like the LU decomposition method, where you basically sort of triangulating those matrices before you invert them. That can reduce it to something proportional to k to the cubed. Those are only partially scalable. So whenever we're inverting matrices, there's going to be a limit. It's not so much the number of observations we're dealing with as the problem is the number of variables that we want to introduce. So I've had conversations with some of my math geek friends about in our department about what's the smartest way to invert large matrices, and I've been told this QR decomposition method is the way to go. But again, becomes complicated as you have large, very large models. So another question here is, so we talked about the useful information. Now, is it always better to have more data? More is generally better. So that's what AT&T tells us. But is it better to have more data, or is it better to have better models? And that's one of those answers. That, well, it depends, right? There's some that argue that data is better than models, because with this also says here, in a nutshell, having more data allows the data to speak for itself, rather than relying on weak assumptions that are unproven. So that might be one argument. Now, let me talk a little bit about statistics here in terms of like size of data and its usefulness. So something real basic here, which still I meet a lot of people that don't quite understand. So like when we're dealing with random samples out of a population, if you have a random sample of a size 1,000, and it's from a population of 100,000, you have basically the same amount of information available, whether it's 1,000 observations from a population of 100,000 or it's a population of 1 million. So it's like, again, the size of the needles and the size of the haystack. The size of the haystack doesn't really determine how much use we get out of it. It's more like how big is your sample. However, a random sample, if you're sampling from a haystack of 1 million observations, it's much more complicated than if you're sampling from a population of 100,000. So there are issues with trying to keep the size of the haystack down. We often talk about random samples. That's when you read in elementary statistics books that say, well, that's the best way to sample. No, that's not necessarily true. Cluster samples often give us more useful information than a random sample of that size, especially when it comes to data mining. So here's an example. So let's say if you had a textbook and you have a randomly selected textbook and you want to try to figure out, based on a sample, what is this textbook about? So I could just pick out a random paragraph from that textbook, and I'll let you look at that paragraph, and you can probably defer from that sample. It's probably a statistics textbook that we're talking about here. Now I could take, so that would be a cluster sample. It's certainly not a random sample. I could also take a sample of 100 words that I pick out randomly from this book. It might look like this. Illustrate, alternatively, sigma, suppose. You could probably defer also from those words that it's probably a probability book, but it's not as useful as knowing an entire graph. And then you could take just completely random samples, just sample characters. Now it becomes even more difficult to infer anything about where did this book come from. So random samples are not always useful. So a little bit more on Moore's law. So the big question here is, will we continue to see a growth of big data in the future? Will Moore's law continue indefinitely in our lifetime, in our children's lifetime, in our grandchildren's lifetime? Will the cost of storage, which is the other assumption, will that continue to be reduced by a factor 2 every 2 years? Will I ever own a cell phone that has a terabyte of internal memory as opposed to 8 or 16 gigabytes, which are not like typical smartphone? Will you have a smartphone with a terabyte? And my answer is probably. Will you ever have a smartphone that has a petabyte? My answer is probably not. Will Intel ever develop a processor that has a 1 terahertz clock speed? My answer is probably not. So just kind of an interesting note here about how when things are getting tinier, like I looked a few months ago up, well, so how much is a typical 1 terabyte hard disk? And you can buy those for about $65, and that was a month ago, so now it's probably $50. So if you do the math here, a terabyte is 1 trillion bytes, so 8 trillion flip-flops. Flip-flop is basically, you know, a few transistors. The physical dimension of this guy here is 82 by 15 by 111 millimeters. So if you look at it in terms of number of transistors per square or per unit volume, you have data like this. So the CMOS technology that's being used, the smallest line of fabrication is about 25 nanometers. So 2.8 times 10 to the 8 minus 8 meters in diameter. However, if you do physics here, or you look at what's the size of a silicon molecule, and the size of a silicon molecule is about in the order of 10 to the minus 10. So you can see we're only like a factor 100 away from a single transistor becoming down to the size of a molecule. So unless we figure out a way to build flip-flops out of electrons, or I don't think physically we can continue to cut things in half, hundreds or thousands of years into the future. So I'll finish up here with just what amusing slide here. What would my house look like if it followed Moore's law? So if in 1984 I was a college student and I lived in a dorm room, it would be about 100 square feet, might look like this. 10 years later, according to Moore's law, I would live in a nice 5-bedroom house. I'd probably be a young professional with a 2-car garage, 3,200 square foot house on a 1/4-acre lot. Now guess what? 10 years later, I'm a full professor. I have a 160-bedroom estate and a 64-car garage and a 100,000 square foot a house on an 8-acre lot. And in 2014, I'll be an associate dean, and I have a house of this size here, 5,000 bedrooms, 3.2 million square feet, 250-acre lot, probably bigger than a New York-sized skyscraper. So just kind of keep that in mind as you think about how fortunate we are with the technology today that is many times bigger than the computing centers that we were dealing with 20 years ago. So some of the challenges I think we will be facing here with the Internet of Things, when inevitably will happen to some extent, will continue to grow big data, and we're going to need more advanced tools. The ratio, in my opinion, of valuable to useless data it's inevitably going to decline. So the size of the haystack will be bigger. There'll be maybe a few more needles, but it'll be more difficult to find them. Reduction in memory cells will eventually, in my prediction, be limited by physical constraints. TV internet communications will eventually become a single technology where we no longer have to search through our TV channels with a remote. And many new applications of big data will need to be developed related to higher education, medicine, and so on. So I'm going to finish up here. Here's some of the credits, people I'd like to thank. Most of all, Professor Wong here for inviting me here. People I've had conversation with over the last year or so on this topic. I have some references here which you won't have time to read here. I'll scroll through them. So I'll open up here for questions here. Thank you.
In approximately how many years do you think that heart monitor and that technology is going to be available for youth?
That's a very good question. I think we'll see a totally different world in the next 10 years. I'll just leave it at that. I don't know exactly what technology will be available, but I think it's inevitable that technology will be available.
I guess it already is available to some degree, like with the defibrillators and things like that. I mean, they have remote transmit. I mean, it's not as seamless as, you know, we're discussing, but the technology's at least there.
Yes.
With the needle in the haystack analogy, if you know the characteristic of the needle, you know what you're looking for, you can find it a lot better, right? So
yes.
Can you speak a little bit about really knowing what you're going for? You're talking about internet, TV communications coming together. I think the world's still struggling to know what is really for.
Exactly, yeah. I heard a quote about the Malaysian Flight 370 where they were saying, if we're looking for a needle in a haystack, we believe we found the haystack. And the haystack is about the size of South Carolina. You know, so now how do you know what a needle looks like? You know, I think is your question. And that I don't think there's a well-defined answer to that. In the traditional data mining is you don't necessarily know what you're looking for when you're doing the mining. You sort of make up what is useful as you do the mining. Just like when we're doing research and we're looking for that interesting article among IEEE's 3.2 million articles, we don't know yet what we're looking for, but we find something useful and say, oh, that looks useful. Now I see 5 other related references that might also be useful. So we get to know more about what the needle looks like as we find one. But my point here is that there's just a lot more things around it that are just not useful, and looking for that bit of useful information is going to be harder. Just like with the heart monitors, so imagine if everyone on the planet is on a heart monitor and it feeds into a supercomputer. We need the tools to be able to get to a point where we can actually automatically call an ambulance when there's not as somebody stops, a heart stops beating, but there's any condition that we've determined statistically is a warning signal that would cause us to call for an ambulance. Yes, sir?
The amount of data is growing exponentially, as you said. So if you consider how much is available today and you compare it with how much was available, say, 5 or 10 years ago, it's at least an order of magnitude, if not more,
right.
Higher. Now, do you see a similar trend in the available methodology to handle all of this? For example, if you open a textbook
right.
that was published today,
yes.
compared to another one that was published 5 or 10 years ago, they are more or less the same.
Correct.
So, do you see a parallel revolution in the methodology?
I see another problem, and that is that we're not going to be able to develop the methodology as quickly as the data and as the complexity of data is growing. And I had another slide which I decided not to show, but that talks about the gap, or the STEM talent gap, that if you look at the kinds of expertise that's needed in today's world, we're not producing enough graduates to meet that need. And I think that gap is going to increase as we need more skilled people to analyze this data. We need more advanced methods. I don't know that we're going to be able to develop it as fast as the complexity is increasing.
Any more questions?
All right. Well, thank you again for inviting me. It's always a pleasure being here, and I hope to see many of you around in the future. Thank you.